Yep. So we have started with recording. Cool. Okay. So the first 30 to 45 minutes we'll just cover the basics and then we will see some problem solving on bit manipulation, okay, and some different ideas, right?
Yeah.
Okay.
Okay, bro.
Okay. So before starting, as usual, what do you guys know about bits? Okay, some information from each and everyone so that I'll get to know where you guys are. Yeah. Start with maybe Manan.
Yeah, so bit manipulation is like every number will have some bit, like two will be zero one.
Okay.
So it's mostly of zero ones.
Okay. Others.
It's a kind of a binary form where everything will be in form of zeros and ones that he has mentioned,
Okay.
and there will be it will be like helpful for the normal manipulations in the CPU stuff like the compiler designing and stuff. I guess.
Okay. Nice. Others. Sahas, Sam.
Yeah. So, as we all know, computer stores in the form of bits. So, we use them for manipulation, like easy calculations or any problem solving.
Okay. So, Sam, anything else you want to add it on this?
Like the same they have told, and apart from that, like a few things I know is like
Oh,
for two powers we will be having one and remaining all zeros,
sorry.
and
Can you repeat
like
that?
multiples of two.
Okay. Uh-huh.
I mean powers of two. Sorry,
Okay.
one followed by all zeros, like
Okay.
1 0, and left shift is multiple of 2 to the power of n,
Oh, no,
and
no, no. I'm
like
not asking all that. Yeah, what that's all. It's enough.
okay,
Okay, we'll go through in that. I just
okay,
about like anything, but yeah, the main thing is why bit manipulation is kind of important sometimes is because you have a number. Okay, so sometimes it's actually difficult to operate on numbers, right? So when it comes to bits, you have only few bits, right? Let's say if you are talking about integer, it's about 32 bits. If you talk about long, it's about 64 bits, right? So in 64 bits, you can actually try to manipulate a long number. So you understand 64 is just a very small number, right? For us. So computer can do a lot of operations in a second and 64 bits is just a very small thing for computer to operate on. Okay, so yeah, we'll see few of the things on bit manipulation. Okay, so let me start with some operators. So couple of operators which we all know but we just want to revise is something like, okay, bitwise and, bitwise or, maybe zor, left shift, right shift, negation, minus. Okay, so we'll talk about each one of them briefly and then we'll move on to the next section. Okay, what does logical and do?
Like it's like if you have two ones, it produces one, and for remaining all it's zeros.
Yes, so let's say we have some number, maybe let's say 13, and let's say we have some number as maybe 9. Okay, so what is 13 represented as? 13 represented as 1, maybe 1101, right? Is it the value of 13 in binary? 8 plus
Yeah,
4 plus
13, 12, 1.
Yes, correct, correct.
yeah, and if we have 9, you represent it as like this, right? So what AND operator does, AND operator actually has like each bit, it will go through each bit, and if it sees that both of them are 1, it just keeps as 1. In other cases, it's like if either one of them is 0 or 1, it just keeps as 0. In case if both are 0, they will keep it as 0. Okay, so this is what you produce, right? And the number is 9.
9 again.
Okay, so one quick thing, one observation is bitwise and of a comma b, okay, is always less than or equals to minimum of a comma b. Do you guys agree?
Yeah.
Yes.
Because whenever the bits are there, okay, if in one number the bit is not set and if in another number if the bit is set, it will eventually turn out to be 0, right? So somehow the number which is being formed will always be less than or equals to the minimum of that number. Okay, so this is one observation. Okay, let's go to bitwise OR. Now what does bitwise OR does? Let's take the same number, okay, 1001. So whenever you have at any position, if you have a bit set, it just sets the bit, okay. That means 1 1 is 1. In the case when both of them are 0, it becomes 0, okay. And then here you see there is 1 and 0 1, and there here is 0. So what's the number formed?
13.
13.
13, right? Again, one
Max
other.
of A comma B.
So a comma b, the bitwise OR of a comma b will always be greater than or equals to max of a comma b, right? This is one observation again. Now you might think why these observations are needed. Sometimes in contest you have to know, okay, this is what is being formed, so can I do something with this relationship?
Okay.
Okay. Next, let's go to bitwise XOR. Okay. So what does bitwise XOR do? So again, let's take the same number 1101, and we have 1001. If if only one bit is set, then it turns that number into 1, otherwise it's 0. Okay. So in this position you see it's 0. Here both of them are 0, so that's the result, we have 0. Coming to this, you have only one bit set, so it's 1. And at this case, since two of the bits are set, you have 0. Okay. Is it fine with bitwise or do you guys want me to explain on this?
Got it.
Got
Yeah,
it.
got it.
Yeah. Okay, so we don't have any relationship on this, but yeah, this is the bitwise OR operator. Okay, let's come to bitwise left shift. Okay, now what is X left shift Y? Sam, you are telling something, right? Can you tell now?
Uh, it's y into
Y into, yeah, Y into,
Hey, you're on mute, Sam.
hello. Yeah, sorry,
yeah.
sorry. Then x into 2 to the power of y. Sorry.
Okay, X into 2 to the power of Y. Okay, so guys
Yeah.
remember, so what happens with left shift is, let's say we have a number. Okay, let's say, so what we are dealing with today's class is generally a number represented in bits, right? So we have, let's say, some number, okay, 1010. And what is this number? It's 2 power 0, 2 power 1, 2 square, 2 cube. I guess it's 10, right? Correct?
Yeah. Yeah.
Yeah. So how the number will be stored in your memory is something like this, right? If it is an integer, you will have 30 or 31 bits with all the prefix set as left or zeros, correct? Now when you are
Yeah.
saying shift left shift my number by 2, what happens? Each of the bit will go by 2. Okay, that means this one will come here, 0 0. You will have 1 here, this 0 will come here, this one will come here, and this 0 will come here. That is, you're shifting each of the bit by 2 times. Okay, and at the end you will have 0 0, right? Now what is this number?
That's 10 into 2 power of 2.
So 10 into 2
40.
is 40.
Yeah.
Okay, so what we have taken x as 10 and y as 2, right? If you keep into the formula whatever Sam has told, 10 into 2 square, which is nothing but 40. And if you see this
Yeah.
binary number, it is nothing but it's 40 itself, right? 0
Yeah.
1 2 3 4 5. So 2 power 5 we have 32, and 2 cube is 8, so 32 plus 8 is 40. Cool.
Yeah. Yeah.
Everyone clear on this?
Yeah.
Sam, Sas?
Yeah.
Yes, bro.
Yeah.
Yes.
Clear.
Okay, so this is left shift, right? Next we have something as right shift, right? So expectations, I mean, what will be the formula?
X by 2 per y.
Right. So we have x by 2 power y. Okay. Now again, let's take the same example. Let's say we have 0 0 1 0 1 0. So what we do is we are trying to shift each of the bit by right side by 2. Okay. So if you keep in the formula, it is like 10 by 2 square. Correct. which is nothing but how
2.
much? 10 by 4 is 2,
2.
right? In case if you are wondering how it is, okay, so when you right shift, these bits are lost. This bit will come here, which is 0. This bit will come here, and again we have all the left numbers as 0, right? So this is nothing but this is 2 itself, right? So we got 2 as
Yeah.
2. Done. Clear,
Yeah.
everyone?
Yes, bro.
Yeah,
Yes.
bro.
Yeah, clear.
Next, what we have is negation. Okay. Now I guess it's kind of simple. Everyone knows it, but still we just want to go through. We let's say if we have a number, okay, what it does is it flips each of the bit, right?
Yeah.
So
0,
uh
1,
0
0,
0. So
1.
this is
Yeah.
the number which you get. Okay. So it just, I mean, uh, there are usages obviously, but I mean, sometimes we don't tend to use a lot. Only there are few things which we do when we try to shift it. But yeah, this is the operator which flips each of the bit. Okay. And
Got
finally,
it.
we have something as minus. Okay.
Okay.
So how now the question to you guys is how does a number stored a negative number is stored in computer?
One's complement.
No, it's not one's complement, right? One's complement is nothing but this only. This is one's complement. It's two's complement, correct?
Yeah.
Yeah.
Yeah, it's not one's complement, it's two's complement. Okay, so let me give you some insights. Say we are doing something as 16 minus 12. Okay, so what happens in computer is it will take it as, right? Can I write like this?
Yes.
Right?
Yeah.
Yeah. Now what is 12? I believe 12 is, let's say, something like this. Maybe like this, right?
Yeah. Yeah.
Right? Now,
Yes.
how to represent a number is it's nothing but it's two's complement, right? So what is two's complement? First we do
One's complement.
one's complement, which is this,
0, 0, 1, 1.
Yes. Plus one.
and just do plus one,
Plus 1.
right? So
Yeah.
0 0 1 0
1, 0,
1 1,
1, 1, 1.
right?
Yeah. Yeah.
Now we have this is minus 12, correct?
Yeah.
Okay. Now what we have is we have 16. So 16 is represented as maybe 0 0 uh, 0 1 0 0 0 0, right?
Yeah.
This is 16. Okay. So what we did is 16 plus of minus 12. So if we add it, and this somehow the 1 is being carried, okay, and it finally it tends to like get discarded, okay, and you have this number. And is it nothing but 4?
Yes.
Yeah.
So are you getting
Yes.
16 minus of 12 as 4?
Yeah.
Yes.
Yeah, so this is what happens internally in computers. Okay, it directly cannot do minus 12, so it represents something like this, and it gets converted like this. Okay,
Got it.
chalo. So these are the basic things, okay, which we just want to know. So is everyone clear on this part at least? I guess there shouldn't be any.
Yeah, bro. Good.
Yeah, clear.
Yeah.
Okay,
Clear.
let's do some kind of bit operations now. Okay, we have many things to discuss on bit operations. Okay, let's say I have I am giving you a number x. Okay, maybe something like this. Now I will ask you, can you guys tell me whether a particular ith bit is set or not? Okay. Now this is zeroth bit, right? This is first bit,
Mm.
second bit, third bit, fourth bit, fifth bit, and sixth bit. Okay. Given a number, you guys have to tell me whether a particular ith bit is set or not. Let's say if I ask you third, is the bit set at third position?
No.
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 Is the bit set at fourth position?
Yes.
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 1.
what you have to do is you have to check for a given number whether ith bit is set or not.
Mm.
Okay. So anyone has any idea like how to check this?
Okay, if we perform AND operation, you'll get one, right? So we can see that number has been particularly set or not, right? Like if it's a zero and we have
With
performed an operation with one.
with which number you will do one? Only one.
Yeah, one.
Okay. So you're saying x. So if I have to ask whether the fourth bit is set or not, so should I do x and one?
Uh, uh, I mean, sorry, that won't be possible because you'll be like having only last bit, right?
Yes.
We need particular bit. Mm.
Okay, cool. So yeah, so this we will discuss it. Okay, how to check whether a particular bit is set or not. Okay. Now what is our x? X is this number, right?
Mm.
Now what is one represented as? Can I say one is represented as some bunch of zeros and one at the last? Will it
Yes.
be stored in our computer like this?
Yes.
Yeah,
Now which bit we want to check? We want to check fourth bit, right?
yeah.
So can I shift this one to this fourth position, or maybe
Okay.
this one to here, because this is our fourth bit.
Yeah, yeah.
Okay, so with the explanation whatever we have seen, how can I
Left to shift.
shift this bit here?
Left to shift by four positions.
Can I write like this?
Yes.
Yeah,
So if I write like this, will it become
exactly.
right?
Yeah.
What is our x? X is 1 0 1
One zero
0
one
0
zero
0,
one zero.
right?
Yeah,
If I do a bitwise and, okay, if I do a bitwise and, check 0 0 0 0 1 0 0, right? After
yeah.
doing bitwise and we got a number y, correct?
Mm.
If y is greater than 0, that means your bit is set. That's the true form. That's the true form of this.
Okay.
Okay. So, guys, anything you want to ask on this? I mean, I'll obviously take another example, but like, are you guys understanding what we have done? We,
Yeah, yeah.
Yes, bro. Bro, just
Yes.
yeah,
for finding fourth position, we need to move I mean, sorry, one only four minus one times, right? Or
no,
four times.
this is one time, this is
Hmm.
two time, this is three time, this is four time.
By the third time only we went to the fourth position, right?
How? So this is our number, right?
Yes.
0 0 0 0 0 0 1, right?
Yeah.
If I do first time,
Like we want to find fourth bit is set or not
this
right
is
now.
the fourth bit, right? This is zeroth bit, Sam. This is zeroth bit.
Okay, index zero.
Yeah,
Okay, okay.
it
Sorry.
is not indexed one. Okay,
Okay, okay, fine.
okay,
Yeah.
From right to left.
yeah, yeah, correct. We go from right to left every time. Cool. So now we have the number as 1 0 1 0 1 0 0, right? Let's check
Yeah.
whether the third bit is set or not. Okay. So this is our x. So what we write in code is x and 1 f shifted by I. I is nothing but in
I.
our case 3. Okay. If
Mm.
this number is greater than 0, my
Set.
Set.
bit is set. Otherwise, it is not set. Okay. So in our case, what will happen? We will shift our 1. This is 1. Okay. We will shift 1 three times. That means we have 1 0 1 0 1 0 0, and we are shifting the 1 three times. So it will be nothing but, right? And you do bitwise and. Now you guys might ask why only we are checking with number greater than 0. The reason, because if you see this number, everywhere it has all the bits as zeros, right? So the only
Yes.
difference is if this bit is 1, then you will get the number is greater than 0. Otherwise, there is no chance. True?
Yeah.
So that's the reason this works, this formula works. Okay. So now if you see, you have all the numbers as zeros. So if the number is 0, that means the bit is not set. Done?
Yeah.
Yes.
Got it.
Got it.
Chalo.
Yeah, got it.
Okay. Next question. Given a number x, again, 1 0 1 0 0 1 0. Can you please, given a number x and a position k, you have to set set that kth position to 1. I mean, you have to set a bit at kth position. So if I tell you, let's say index 3, then the number should look like 1 0 1 1 0 1 0. Okay. You see the index 3, it got, I have set it as 1.
Okay. You can perform or operation or XOR operation.
I think XOR operation is
Uh, if I give you index 4, it should be 1 only. It should not become 0 because we are setting the bit. What do you mean by set a bit? Set a bit
Okay.
always turn a 1. Okay. So
okay.
Okay.
So in that
Then
case,
we
you
can
can take
or
one and
Or operate.
yeah, left
or in left
with
shift.
K,
okay. Or with
Left
left
shift.
shifting of one with K.
nice.
Mm.
So, are you guys getting this? I mean, what we have done,
Yeah.
we have taken a number, we have taken a number 1, okay, and we are writing x equals to x or 1 left shift k. So, what we did,
Yeah.
we took the 1, we shifted that into k left position, and we made it as or, because if there is one, at least one in our binary representation, then it will set the final representation as 1, right? So, this
Yeah.
works. So, is everyone clear on this?
Yeah.
Yeah.
So,
Perfect.
Yeah.
Good. Now, same question. Okay. We have a number x. Given a position k, you have to unset that bit. Not set, you have to unset. That is, with respect to whatever it is, you have to make it 0. Yeah. This is pretty good. Okay. You got the point, right? We have a number 1 0 1 0 0 1 0. Let's say I say index 4, then the number should be have turned unset, have turned off.
Um, yeah. So we can take
yeah.
one and move it with K
Okay, so you said 1 left shift
XOR.
k. Okay.
and finding
XOR.
its negation
Nice.
and now and operation
With
with X.
a brilliant man. Good, good. This works. So you want to see this in action? Others, you want to see this in action, or do you think this works?
Action.
Okay. Sahas, he doesn't have trust, my man.
No problem, bro.
Okay, see. So what happens? We have this number, right?
Yeah.
And what we have is Sahas told, let's shift this to k position left, right? So in our case, it is nothing but 0 0 1 0 0 0 0, right? Do you guys agree with
Yeah.
this number?
Yeah.
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 What
Yeah.
does negation do? Negation flips the bit, right?
Yeah.
This is 1, this is 1, this is 0, this is 1 1. What is this? 1 1, right? Ah, wait, you guys got it, this one?
Yeah.
Now you have this number x, you have this negation of 1 left shift k. Now if you do and, can you see this bit will always become 0 because there is a 0 here,
Yeah. Got it.
right? So we want to turn off this bit, right? And others, since you have the number as 1, it will always resulting in the same bit as x. Okay.
Okay.
Manan, Sam, you guys are clear?
Yeah.
Yeah. Clear, bro.
Yeah.
Nice. Okay. So we have done set, unset, check. The next thing is, yeah, flip, flip ith bit. Given a number, something, let's say if I take If I ask you some index, if it is 0, you have to make it 1. If it is if it is 1, you have to make it 0.
XOR operation.
XOR operation, yes.
Cool, cool, nice. So if we do, hey man, you guys are good at bit manipulation, no? Right?
नसी ने ये फॉर्मूला भी देखते देखते पता चला ठीक
Okay.
है
So what we do with XOR actually, this is a very good property of XOR, that it flips the bit, right? So when you have 1 0, it is 1, right? So if you do a XOR, it always flips the bit, because in one left shifted with I, you will have one available with you, right? And if the bit
Yeah.
is 0 or 1, when you XOR with this particular bit, if it is 0, it will become 1, and if it is 1 with 1, it becomes 0. So that's the power of XOR. Cool?
Yeah, got it.
Clear?
Yeah.
Hmm.
Yes.
Yeah, ठीक है वो.
Chalo, nice. Next thing. Given a number n or x maybe, okay, count number of set bits. Yeah.
I remember one
Uh,
formula, bro. In Java, we will be having some inbuilt function.
Yes, that is bit count.
Yes, yes.
Yeah, nice. That's a good thing to know. Okay, but yeah, we will not use library. We will do manual one. But yeah,
Yes.
that's an operation. Correct. So bit count helps you on that. Others brute force. Let's not optimize it. Let's go for brute force. Okay. How many of you can solve in brute force? Given a number x, you have to count number of set bits.
Yes, like by mod by x.
Mod
It,
by x
sorry, mod by 10.
100?
Mod by 10. 10.
No. Why mod by?
Sorry, 2 2. This is bit rate. Sorry.
Yeah, bro. We
Sorry,
count.
sorry. Uh,
Okay.
mod by 2. If it is equals to 1, we increment the count.
Okay.
X equals to x by 10.
X
Next.
equals very nice. X equals to again x by 10, right?
2 2.
Yeah.
Sorry.
Yeah.
Actually, for reversing things, we will be doing the same, right? That's
Yeah,
the
yeah. Okay. No worries. But yeah. So guys, did you guys understand the brute force? Brute
Yeah,
force is while loop. While loop may what you write, you have x greater than 0, right? If x modulo 2 is 1, that means there is a set bit available, right?
set bit.
Count
Yeah.
bit. And you make x by or equals to 2, right?
Mm.
Manan, is it clear?
Just show me first one, like the X percentile to one. That's it.
This one?
Only that one.
Okay, let's take a small number. Okay, maybe 10. Okay, is 10 greater than 0? Yes.
bro.
Yeah.
Yeah, bro.
How fast you are writing
Bits.
that shit?
How fast you are?
Writing that bits, bro. Like, do you remember or any trick?
8 for the one.
రాసి రాసి అలవాటు అయిందిరా.
Yes.
Mm.
Okay, okay. So, is 10 greater than 0? Yes, it is there, right? Manan?
Yeah.
Yeah, it's for you.
Yeah.
So,
Hmm.
is 10 greater than 0? Yes. But
Yes.
if you see the last bit, it is 0, right? That means
Hmm.
we don't have a set bit. So
Hmm.
how can you check that this is actually uh, if it is an odd number, do you know this? All the odd numbers will have last bit as 1, and all the even numbers will have last bit as 0. Okay, so in
Hmm.
our case 10 is greater than 0 and 10 is even, correct? That
Hmm.
means we don't have a set bit available, right?
Hmm.
And then
Yeah.
what we do is we do 10 by 2, which is nothing but 5.
Hmm.
How 5 is represented? You just remove this bit, that's all.
Hmm. Okay.
So now you have an odd number, right?
One number.
That means one count.
Hmm.
And
Okay.
do 5 by equals to 2, which is nothing but remove this bit.
Very good.
Now we have
Okay.
2. 2 means again it's an even, that means
Even.
we don't have done. We have 1. 1 is an odd number. So 1 by 2 is 0, and you are done, and you finally have count as 2. Cool.
Hmm. Oh, yeah. Cool.
Chalo. So this is one thing. Now, quickly, someone tell me the time complexity of this.
Log in now.
Log into the base.
2.
Nice. Now, can you guys relate with binary search and tell me why it is login
Because it's reducing half, right, by for every search.
X equals to x by
equals
2
to
power n. 2 power
yes,
n, like like you told one formula, no?
yes,
Binary
correct.
search.
So what you're doing is every time if you see this number 10 became 5, 5 became 2, 2 became 1, right? So it's almost log n operation. Okay, that is dividing each time by half. Got it?
Yeah.
Okay. I'm expecting Sahas, Manan, you guys got the point, right?
Yes, bro. Yes.
Yes, yes.
Okay. Now, but we will not use this because even though login is super fast, we want to do more faster than this. Okay, so there is this very famous formula which is, I guess, I don't remember the exact name, but it is something as Bunningen, something like that. Okay, so what he has said is, I mean, this you kind of memorize for now, because even I have memorized in my during the learning part. Okay, while x is greater than 0, what you do is you do c plus plus, that is count plus plus, and write x equals to x and x minus 1. Okay, this is it. That's all. And finally,
Mm.
if you return C, it is your answer. Okay. Now, obviously, I'll explain why this is working, but this is very short code, right? You guys can remember this.
Yeah.
Okay. So, do
Yeah.
you
Got it.
know how this is working? I mean, how this is very good.
Got it.
So, let me take one example and explain you. Okay. What is this number? Is it 20?
2 per. Yeah. 12 plus 8.
Yes. Yes.
20. No,
No,
C.
4 or 16. 16, I guess, right? 2 plus 0.
Sorry,
No. 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 20 only.
20.
Okay. Yeah. 14, right? Sorry. 16. Sorry.
Okay. Now, the thing is, what this expression is doing. This is the important part, right? Now, this is x, correct?
Yeah.
If you do x minus 1, what is x minus 1? 50, 20
Uh,
minus 1 is
19.
19. So, can I write 19 as 16?
Yes.
I can
Yeah.
write, right? And when you do and, what happens? You have 0, 0, 0, 0, 1.
1.
16.
It is nothing but 16. If you observe this carefully, what you're doing, the last bit, you're removing it. Did you get the point?
Yes.
The
Yes.
last significant bit, you're removing it. Removing in the sense unsetting that. Okay. Now again, x is greater than 0 because we have 16, right? So our count will become 2. Initially it became 1, then count became 2. Now we have 16 minus 1 is how much? 15?
Mm. That's
Yes. Correct.
15.
exactly.
If we do and, can I say this bit will be removed now?
Yes.
Yeah.
Yes.
Zeros.
Zeros. So
Yeah.
this number is 0. Now 0 is greater than 0? No. So
No.
you are done. So what you have done is you have removed the last significant bit again. Correct?
Yeah. Got it.
Got it right? So
Yeah.
what this operation does is every time it removes your last set bit. Okay.
Okay.
Now what will be the time complexity of this? So can I, if let's say if this is the number, how many
Mm.
times this loop will work?
4.
No, 4 or
5
6?
6,
times.
right?
5 time, right?
Yes.
Yes.
5.
Right. So can I say big O of number of set bits?
Yes.
Yeah.
So is it better than log n?
Yes.
It is, right? It's better than log n. So this is the formula of
Okay.
Bunningen or whatever. That every time you remove the last significant, least significant bit from your number. So this code works in big O of number of set bits of a number. And in case if you are given even a long number, you will have only 63 bits set. So only it takes 63 number of operations. That's all. So how quick it is. So did you guys clear on this part?
Yeah, bro.
If you have to calculate number of set bits, can you guys do it?
Yes, bro.
Yeah.
I'm not writing the code
Yeah.
because this is this much only, right? So I guess
Yeah.
no need to write.
It's okay.
Anyone want me to write or
No, it's okay. It's okay. Got it.
No, no.
okay? So this is the basics of bits. Okay. Now this is the only thing we have in bits operations. Now we will learn a. Okay. Before that, maybe I can tell you something. On, how many of you know this? This is XOR.
Yeah. Okay.
Zero.
Plus 101.
Zero.
You know this property A XOR A equals to 0,
Yeah.
right?
Yeah.
Because
Okay.
each bit will have same bit, right?
Same.
That means
Yeah.
in the XOR, if we have same bits, then it is 0, correct?
Zero. Yeah.
Yes.
A XOR 0.
Yeah.
If A equals to B XOR C, then B equals to
A or C.
nice. Now how it is coming? So we have A equals to B XOR C, right?
Hmm.
Correct.
Yeah.
So what you do is you uh, mm, take XOR C on both sides, right? I have taken XOR C on both sides. Okay. So this will cancel off, correct? So you have B equals to
Yeah.
A XOR C.
Okay. Got it.
Got it? So in
Yeah.
bitwise XOR, remember you can uh, interchange the positions.
Hmm.
Clear, Sam, Sahas, Manan?
Yeah. Clear.
Yeah.
Yeah.
Clear, bro.
Or do you guys have anything to ask?
No.
No.
No. Got it.
Okay. Now, okay. Let's say uh, you have some fixed length bits. Okay. Fixed length, probably let's say 30. Okay. So we have a 30 bits available with us. Okay. 30 fixed length bits. So what you have to check is whether all the given a number x and it is a 30 length bit, whether all the bits are set or not.
Okay. If we do a XOR operation, we'll get zero, right? If the result is zero, which means the all was set.
No, the question is, let's say for this example, let's take we have only 4 bits. Okay, only 4 fixed length bits.
Okay.
Is all the bits set in this?
No.
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 Is all the bits set?
Yes.
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 So given a number x, let's say only of length 4 or length 3 or length 2 or length 1, but the fixed length of 4. Okay, can you tell me whether all the bits are set or not? So this is the question. Think for a
Yeah.
minute and then tell the answer. Don't be in a rush. We are not here to complete, we are not in a contest. Done?
One thing we can do is count the number of set bits.
Okay, nice, good. So Yeah, that's a good approach. We can calculate the number of set bits, and if the number of set bits are 4, then we are done. Good.
Yes. Yes.
Nice. So that will take a time complexity of big O of set bits, right, Sar?
Yes. Yes.
But we want to do it more better.
Okay.
Yeah, that's a good approach. I mean, that works obviously. Others
If we do negation
of which one? X.
x,
Okay.
it should be equal to 0.
Negation X. It should be equals to 0. Hey, brilliant man. It's working, right?
Yes. Yes.
Hey, nice. Nice, nice. Hey, honestly, I didn't think of this. I mean, it's actually working. Correct. Okay. Do we have any counter test cases?
He said all bits should be set right.
Yes, yes, yeah, that's nice. Yeah, yeah, Manan, it works actually. Okay, so maybe I can try to think of any counter test case. But I guess it does not exist because this works. If it is zero, then yeah, it's true. Okay, so what actually I was trying to do is because in sometimes in I see in bitmask we use this kind in bits we use this operation. So I asked you 4 length bit, right? So can I write one left shift 4 minus 1? What it will give me? It will give me all the number as set bits, right?
Yeah,
Yes.
So what will happen is you have 1. What you did, you took left shifted by 4, which is nothing but this, and
yeah,
then you did minus 1. Minus 1 means all of them will be like this.
yeah,
Okay, now given a 4 length bit, let's say 1010, if I do and, if it is not equals to this number, then all the bits are not set, correct?
yeah,
So this is not equals to this, right?
mm,
So, and we have this number and the given number is 1111. If I do and, I am getting all the numbers as 1, right? That means
yeah,
all the bits are set. So you can probably write it as x and 1 left shifted by I minus 1. If it is equals to 1 left shifted by I minus 1. Can I say all my bits are set? Confused?
yeah. A bit because
Bro,
we
what,
got the negation right.
Yeah. Okay, okay,
bro,
fine.
what is this minus one concept like? Why?
Minus 1 concept, Sam, is okay. So when we have uh, all the numbers, okay, you said something in 2 powers, right? If it is a power of 2, you can represent everything it like this, correct?
Yeah,
What is 1 left shifted by I? It is nothing but 2 power I only, right?
yeah,
Agree?
yes, yes.
So when I do 2 power x or 2 power I minus 1, can I say it will be nothing but this only?
I'm not sure, bro.
Okay,
I don't know this.
okay. So if you write it on pen and paper, you will see that.
Okay.
uh, okay, so first thing before going,
Like it means like all zeros will become one and one becomes zeros.
yeah, because in 2 power x, uh, all the numbers will be in the form of 1 and bunch of zeros every time,
Yes.
right?
Yeah, yeah,
So when
yeah.
you do minus 1, what happens is this number will become 0 and all the numbers will become 1.
Okay, okay, fine.
Okay, and the cool fact about this is if you do a bitwise and, if the number is turning out to be a 0, then x is a power of 2.
Mm-hmm.
Given a number x, check whether it is a power of 2 or not. You can simply write it as, if this number is equals to 0, it's a power of 2.
Left.
Why? Because if the number is in power of 2, x minus 1 will be like this only, right?
Yeah.
And when I do bitwise and, all the numbers will be 0. True?
Yes. Yeah.
Yeah. Let comes to some other number which is not a power of 2. This is nothing but 10, right? If x minus 1 will be 9. अरे हाँ ना बोलो भाई तुम लोग.
Yeah, yeah.
Yeah. Yeah.
Now if I do and, what will happen? You will get it as,
1 0 0
All
0 1.
zeros.
this is not equals to 0. That means x is not a power of 0. Okay. So a quick hack is, given a number x, if you have to check whether it is power of 2 or not, you can just do x and x minus 1. Okay. Okay.
Okay.
So so do you want me to teach this? I mean, obviously negation x works, but this is something which I use in problems. Okay. Okay. Let's see. I am not taking this now. Maybe when it comes, I can take that. Okay. Yeah. So the next concept will be, okay. So are you guys clear till this part, everyone?
Yeah, yeah.
Okay. Next, this is a very important concept. You guys would have heard. I'm not sure, but yeah.
Bit masking.
Hey, we'll stop the recording now, and then we'll start with new one.